Welcome to the session by Vladik Khononov on balancing coupling in software design. Please welcome the speaker.
Guten Tag. That's all I know in German, by the way. So my name is Vlad, or Vladik Khononov. Now you can pronounce my last name however you want. At this stage, I don't care anymore. Whatever works for you, I'm fine with that. So I'm a software architect. At the moment, I work for a company called Do It International. It's a cloud computing reseller, and we offer consulting services to our customers. At Do It, I'm a senior cloud architect, and my job revolves primarily about explaining to people why Kafka is not an event store and why cloud vendors' blogs are the worst. Okay, they're not sponsoring, so why AWS blog is the worst place to learn about CQRS. I'm also an independent consultant, and when I wear that hat, I specialize in, surprise, surprise, domain-driven design. Speaking of which, this is my latest book, Learning Domain-Driven Design, and I have a question for you. Anybody here already have it? And keep your hands up if you liked it. I saw you. Cool. For those of you who don't, I know that we're at the end of the second day, and you've probably been learning a lot today. So we need to shake things up. And to do that, let me introduce to you, this is DDD coin. This is a new currency. It is more stable than euros and bitcoins combined. One ball will get you a copy of the monkey book in German. So right now, I'm going to throw some balls. If you catch a ball, you get a book. Now, if you already have it, or if you don't speak German, then pass it along to someone for whom it will be more useful. Ready? Okay, first, second, third. Okay, come to me afterwards, you will get your book. Okay. So today I'm not going to rant about domain-driven design, but another topic that is really fascinating for me. And coincidentally, it's also the topic of my upcoming book, Balancing Coupling in Software Design. Please don't ask me when it's going to be published. That's a very painful subject. We'll talk both about pain and about when it's going to be published a bit later. So for now, let's start. So here's the thing. There is one quote that lately I've been using almost all of my talks. So in this presentation, I was thinking, hey, why should we wait for the end or the middle? I'll just put it right there on the first slide. So here it goes. Ruth Malan says, system design is inherently about boundaries. What's in, what's out, what spans, what moves between, and it's about trade-offs. It reshapes what is outside just as it shapes what is inside. And I want it here on the first slide because it really outlines the overall topic of this presentation, system design. But more specifically, the relationships that span across boundaries, the relationships that define not only what goes across the boundaries, but also what has to stay inside of those boundaries and what can be extracted. And of course, relationships involving the thing we fear the most, coupling. And we've always been told that coupling is bad. Coupling slows us down. It cripples our systems. When working on a code base that doesn't cooperate with us, that resists all changes we're trying to make, we are blaming it on coupling, of course. So, as a result, not surprisingly, what do we want to do about it? Of course, we want to decouple everything. We have to break everything apart into those tiny services, classes, serverless functions, or whatever. The motivation is always the same. We want to be able to change each of those smaller boxes independently. But what results are we getting by following this somewhat simple reasoning? Well, in many cases, we go from coupled piles of code to distributed piles of code. And that's not surprising because, as Matthias says here, going for as small as possible is almost universally a bad advice in software design. Also, as Nick Thune puts it, there are many useful and revealing heuristics for defining the boundaries of a service. Size is one of the least useful. And yet, we keep on doing that. So I know it may sound controversial, but instead of fighting coupling, I want to show you a different way of thinking about it, and I will even try to convince you that we can use coupling as a design tool. So in the next 40 minutes or so, we'll explore the nature of that scary beast that we call coupling. We're going to analyze what it is exactly and how coupling manifests itself in different dimensions in software projects, and ultimately, how you can use that knowledge to design modular systems. So, what is coupling? So, if we go to the lexical origins of the word, it takes us all the way back to Latin, where it was composed of two words, co and apere, meaning coapere, fastened together. So, in other words, if two things are coupled, they are connected, right? And that makes coupling a universal phenomenon. It is everywhere. This clicker, it is coupled to my computer. Organs in our bodies are coupled to form us, living organisms producing code, or in my case right now, like producing insane amounts of adrenaline. Anyway, cars, computers, cities, organisms, companies, for that matter, any kind of system is held together by coupling. You cannot build a system if all of its components are disconnected. This is just a collection of some parts. Simply grouping them together in some boundary doesn't provide any value. It's just a bunch of fully independent and decoupled entities. But that's not a system. For a system, we need these relationships. We need these connections between the components. So coupling makes that overarching system greater than the sum of its parts. Therefore, it makes no sense to completely decouple everything. That will destroy the system. So coupling, it's rather an inherent part of system design. Instead of trying to eliminate it, it's more reasonable to evaluate those interconnected intercomponent relationships and see if they're working for us or against us. And once we have that information, we can use it to rethink our design decisions where needed. For example, let's say we have these two coupled components. It doesn't matter how they're coupled. It can be synchronous or asynchronous. It doesn't matter what these components are. They can be services or classes, whatever. The thing is that downstream here references and thus depends on the upstream component. The arrow between them, that relationship, it defines how these components are integrated. It defines how change in the upstream component is likely to break the integration and cause cascading changes in other parts of the system. As Michael Neigert says, coupling defines the components' degrees of freedom. How freely the components can change without affecting the rest of the system, without affecting other components. In other words, coupling defines what changes can we make in the upstream here without being afraid to break the integrations with other parts of that system. The interfaces that are used for integration, they have to enable some movements or some changes, but they also have to prohibit others. As in this example of Lego blocks, they're designed to enable certain types of connections, but they also prohibit others. And this clear definition of that integration interface, it allows introducing new shapes that can work with all the existing Lego blocks. Now, it may sound limiting, but we actually don't need unlimited degrees of freedom. That would render any system overly complex or simply unusable. For example, I don't want this clicker to be coupled to my phone, my car, or to that chair for that matter. That makes no sense, right? Unlimited degrees of freedom is just chaos. So we want to make some integrations and changes safe while restraining those that we are not interested in. In other words, we want to align the allowed degrees of freedom with our needs and expectations of future changes in the system that we are designing. And that makes coupling a first-class design decision. So going back to Ruth Malan's quote, we want to design what spans and what moves between the boundaries in a way that's going to enable only the changes and movements that we actually need. And it will prohibit changes that we are not interested in. To do that, we have to understand the dynamics of coupling, how it works, and how it manifests itself. Now, the thing is, coupling is not some unidimensional phenomenon, like you can just look at it and give it some number, some grade. It's more complicated. Coupling works in multiple dimensions, in the dimensions of space, time, and the combination of these two, gravitational force, if you will. So let's go over these dimensions. Let's see how coupling works in each of them. But I have to warn you, the first one, strength, that's going to be the heavy one. That's like, we're going to spend most of our time there. So the effect of strength is probably also most obvious, right? It reflects source of gravitational force that pulls components together. It defines what is the impact of a change in one place in the system is going to be on other components that are coupled to it. The higher the strength, the more cascading changes are going to follow. As our industry evolved, a number of models were introduced to evaluate levels of strength, namely coupling in the structured design methodology and a model called Kinescence. Who here is familiar with structured design? 3 hands. That's a record. And, well, Kinescence, who attended Marco's talk yesterday? I see. Anyway, we're going to briefly go over all these models. We're going to see the differences between them, analyze what each level of these models means, and I have to warn you, no need to try to memorize all this stuff. Again, lots and lots of topics, and I know we're at the end of the day. Don't try to memorize it. Instead, I'll tell you when it's time to start memorizing things, okay? Just focus on the essence of these models, what they're trying to reflect, and what are the differences between the different levels. Later on, we're going to combine them into a different framework. So, structured design methodology, it was introduced back in the 60s. You won't find these books on Kindle, but it's fascinating to see that if you do find them and you read about the issues software engineers were facing back then, without the context, you won't be able to understand whether you're reading a book from that is 50 years old or it's a week old, because the issues are still the same. We haven't really learned anything. So back then, to evaluate coupling, that structured design methodology proposed 6 levels of interconnectedness: content, common, external, control, stamp, and data coupling. Now, this terminology, it may sound somewhat unintuitive, and that's because it is based on languages such as COBOL and Fortran. Let's see what they mean. So the first and the strongest level of coupling is content. The idea here is simple. A module uses private interfaces, or in other words, implementation details, in order to communicate with other components. For example, today, we can use reflection to access private fields or execute private methods. They are private for a reason. They were not intended for integration. Once we are using the magic trick of reflection or some other death-defying maneuver, that's content coupling. Modules are common coupled if they communicate through a globally accessible memory space. This shared memory space is an unstructured global binary. In our days, the example of common coupling would be two services working with data stored in S3 bucket, for example. There is no schema there. You can put whatever you want, but they are communicating by exchanging the data. So both components have to duplicate that business logic that encodes and decodes the data that is being written. Another example would be using a database which is schemaless. That schema it belongs somewhere. It will sit in the code that writes to the database, as opposed to, for example, working with a relational database that enforces that schema. So this integration interface, it's quite implicit. That logic is duplicated into places, and when it happens, it's easy for the two implementations to go out of sync. One engineer changes something, and it's not coordinated with the second one, and that's where fun begins. Slightly lighter is the level of external coupling. Here, instead of using an unstructured memory space, the modules are communicating by sharing a global variable. That variable can be a primitive, or it can be an array of primitives, but it is still a shared memory. But at least here, the interface is much better documented. We have the schema. We know exactly what goes into that shared memory space. Example from our world would be using a database that enforces schema. Those components don't have to hold that logic in their code. Control coupling. This one happens when one module dictates to another one how to do its job. Or in other words, the business logic is spread across multiple modules instead of being implemented in one place. Stamp-coupled modules are communicating by exchanging data records. These records are data structures containing way more information than is actually needed for integration. So let's say I have a component, and I'm asking another one for an email address of a customer. And instead of getting the email, I'm getting like a whole customer record with dozens of fields. So I get way more information than I asked for. And sharing this extraneous information, it makes the consumers more sensitive to the changes in those data structures. And overall, it doesn't really reflect the integration protocol. It reflects the model that is used internally in that component. And finally, data coupling. This is the lowest and the most desirable level. Here, the modules are communicating by passing arguments with integration-specific data only. They're not sharing any extraneous information, the minimum that is needed for the integrations to work. So overall, these levels reflect how much implementation details are shared across boundaries. From content coupling, where all the implementation details, all that knowledge is shared across the boundaries, to data coupling, where the integration interface is both minimized and explicit. Now, these levels of coupling were introduced back in the 60s. In the 90s, Miller-Page-Jones proposed a different way of measuring coupling, which is more adapted to the object-oriented programming paradigm. And you've heard about it. It's called Kinescence. So this word comes from Latin, and it means having been born together. According to Miller, components are defined as born together if a change in one component necessarily requires a change in another one, or if you can postulate a reasonable change, and reasonable is the key word here, a reasonable change that would require both components to change. Compared to structure design, here we have almost twice as many levels, and they're categorized into two types, static and dynamic kinescence. Let's start with static, of course. These levels, they can be analyzed just by reading the code. They reflect compile time dependencies. And the lowest one is the kinescence of name. This one means that two variables need to have the same name in order to reference the same thing, in order for the integration to work. For example, passing named arguments, or even using a hash map to retrieve a value. You need the name, the key of that value in order to get it. So that's kinescence of name. Kinescence of type or of class, as the name suggests, means that types of variables have to match as well. For example, you have to know whether you should pass an integer or a float value. If you pass an incorrect type, the integration is going to break. Kinescence of meaning happens when conventions are used to assign meanings to values. A trivial example is what we call magic numbers, as in this example right here. Status equals 7. That knowledge of what 7 actually means and how it affects the business logic, it has to be spread across the modules that are using it for integration. Both have to know what 7 means. That knowledge is duplicated. Next, kinescence of algorithm. And this one happens when two modules have to agree on the use of a specific algorithm in order to understand each other. For example, when two modules are communicated by passing encrypted data, they have to agree on what encryption algorithm they are going to use. Now, an important point here, it's not about duplication of code per se. It's about an agreement they have to make about an algorithm that both are going to use in order to decipher the incoming and outgoing data. For example, implementation can differ. One can be written in Python, the second one can be written in Node.js, but they still can use the same algorithm in order to understand each other. Also, they should, even if they are not duplicating the implementation of that algorithm, for example, both are written in the same framework and they are just using standard library, that's still kinescence of algorithm. They need to know what algorithm they have to use in order to understand each other. And finally, the highest level of static kinescence is the kinescence of position. This one means that instead of passing values by names, they are communicated as an array where the meaning of each value is defined by its position in that array. Such integration interface is, of course, implicit, and it makes it easy to make a mistake, to put a value in an incorrect place, and suddenly, who knows what's going to happen later on at runtime. So that's the highest level of static kinescence, kinescence of position. So again, I want to remind you, no need to try to memorize all this stuff, okay? Focus on the essence, what they're reflecting. What are the differences between these levels? Why kinescence of position is way more implicit than kinescence of name or of type. The second type of kinescence is the dynamic one. These levels, they can be identified by examining the runtime behavior of a system. Or in other words, if static kinescence reflects compile time dependencies, here we're talking about runtime dependencies. And the first level of dynamic kinescence is execution. Here we have a set of operations which must be carried out in the given order, like a recipe that have to be followed precisely step by step. For example, when working with a database, you have to open a connection and then you have to close the connection. If you change the order, if you close the connection and then you open it, but guess what? It's not going to work. And that makes these two methods kinescent by execution. A higher level of strength is the kinescence of timing. And here we have an operation that should be executed in a set period of time after something else happens. Going back to the example of a database, let's say that we open a connection and nothing happens for 30 seconds and we want to time it out. Once we define that we want the timeout to happen in exactly 30 seconds after nothing happens, it makes the open connection and timeout connection methods kinescent by timing. If, for example, we time out the connection earlier than 30 seconds, that's not what we wanted. Also, if we time it out in an hour instead of 30 seconds, again, that can break the system. So these two methods, they're kinescent by timing. There is the set period of time after which another action should be executed. Almost the strongest level of kinescence is kinescence of value. And here we have values that have to change together, meaning that there are some business rules or invariants or constraints that dictate that these values, they have to change atomically. They have to change together, or otherwise the system will end up in an inconsistent state. A trivial example, think about a data structure representing edges of a triangle. Changing the value of one of the edges necessarily requires you to change at least one of the other edges, because otherwise the triangle is not going to be mathematically correct. And that makes that data structure kinescent by value. And finally, the highest level of kinescence is the kinescence of identity. And here two objects must reference the same instance of another object in order to function properly. And a trivial example here would be having two modules or two components working with the same set of data. For example, they're both modifying the same set of data. Right now, let's ignore whether it's good design, bad design. That's the property of this level of kinescence. They have to work on the same set of data. If we give each component its own copy, then they're not synchronized, the system doesn't work. It goes against the business requirements. So these are the levels of dynamic kinescence. The lowest one, execution, in which operations have to be executed in a specific order. And the highest one is the kinescence of identity, in which a third object or a third memory space is shared between multiple modules. Now, it may sound as if we can find some parallels between the structure design's coupling and kinescence. But actually, these models, they're actually a bit different, and in fact, both are quite challenging to be used in our day-to-day. First, it's not really convenient to use terminology from languages such as COBOL and Fortran. If today you're going to say to someone, well, that interface introduces external coupling. Let's reduce it to control coupling. That will definitely make you sound smart. Believe me on that one. But no one will get what you mean. Second, both these models, they have their blind spots. For example, let's say we're going back to that example of using reflection to access a private variable or execute a private method. Where are we on the structure design scale? Help me out. Content, exactly. Yeah, we're using private interfaces. But in order to execute reflection, what do we need to know about that private variable? Name. And that puts us in this amazing place on the Kinescence scale. Awesome. Another issue with Kinescence is that it doesn't address extraneous data that can be passed in integration interfaces. For example, it is addressed by structure design, stamp coupling versus data coupling. And finally, the biggest issue is that if we have duplicated business logic that have to change because of the same business requirements, it isn't really reflected in any of these models. And I want to reiterate, that's not Kinescence of algorithm. Kinescence of algorithm only means that the two methods have to agree on the use of some algorithm to understand each other. That's the point. If we duplicate the business logic in multiple places in the system and they're not connected to each other, there is no Kinescence there. We cannot even use that model to compare them, to evaluate them. And also, duplicating code, for me, it sounds like it should be all the way there on the top, like the worst level of coupling. And we know that it isn't. Algorithm is there, almost at the bottom. So, since structure design was introduced in the 60s, Kinescence was introduced in the 90s, and we're in the 20s. That makes this cadence of 30 years perfect time to start thinking about a different model of evaluating coupling strength. So, remember I told you that I will tell you when it's time to start memorizing stuff? Now's the time. So, I want to show you a model that I've been using for quite a while. Integration strength. I find it way more practical, find it more useful, and I want to share it with you. Basically, it's a remix of structure design's approach and Kinescence with a focus on different levels of knowledge that are being shared between components. It consists of only 4 basic levels: implementation, functional model, and contract coupling. As the name suggests, implementation coupling is the highest level, and it's synonymous with structure design's content coupling. Modules are integrated through using private interfaces, and thus they introduce dependencies on implementation details. It just sounds to me that implementation coupling is somewhat more easier to understand than content coupling. Now, needless to say that this integration method, it's fragile and implicit. When this happens, we have to assume as if all knowledge about the implementation details are shared across boundaries. Next one is functional coupling. And this one means that the connected modules are implementing closely related business functionalities. Its practical implication is that the same business requirement is going to trigger simultaneous changes in both components. The extreme example of functional coupling would be two modules implementing exactly the same business logic. When the requirements for that business logic change, both modules have to change together. And as I said before, functionally coupled modules don't have to be connected physically. No, even if that logic is implemented in unrelated parts of the system, they still have to change together. And that makes this relationship quite implicit, because if there is no physical connection between them, well, good luck remembering that you have to implement a change in multiple places. And even bigger good luck to whoever is going to join the team in a few years. A lower level of integration strength is model coupling, meaning that the components are based on the same model of the underlying business domain. And this level is somewhat similar to structure design's stamp coupling. It means that we are sharing way more than is needed for implementing that integration. Now, when you have to change that model, you have to change it in multiple places. And that makes it more difficult to improve that model and to evolve it over time. And since we are at a DDD-related conference, I don't have to talk about the importance of evolving your models, right? Cool. Finally, the lowest level of integration strength is contract coupling. Here, the components are integrated through an explicit integration-specific model that is decoupled from their implementation model, meaning that the implementation can evolve independently of that integration contract. Of course, as long as it can be translated to the same contract. So it gives way more freedom. So these are the four levels of the integration strength model. They reflect the amount of knowledge that is shared across components' boundaries and how implicit or explicit the integration interfaces are. Implementation coupling shares the most knowledge about how that upstream is implemented. Functional coupling reduces the knowledge that is being shared from how to what is being implemented. Model coupling reduces it further to the knowledge of the model that's being used by the upstream component, the model of the business, its business domain, and contract coupling minimizes the interface to the bare minimum that is needed for that integration. Now, let's say that we have two components and we have implementation coupling between them. Does it mean that the design is necessarily bad? What do you think? Yes? No? It depends. Consultants. Yeah, it depends. Well, actually, we are still not ready to answer that question. We have to explore more dimensions. And the next one is the dimension of space or distance. So turns out the physical distance, physical location of components, it also affects their levels of coupling. Because the connections between components that can be implemented at different distances, these distances are related to what we usually call levels of abstraction. We can have coupling between individual methods, classes, namespaces, components, microservices, or whole systems. But the question is, what do we have here on this vertical axis? What do you think? Give me some ideas. Strength. Close, but what else? Sorry? Yeah, that's very close. Yeah. Yeah. Cool. Thanks. So first of all, it's the coordination that is required to implement a change. The longer the distance between the elements that have to be changed together, the more coordination effort is required to actually make that change. In other words, the cost of a change is proportional to the distance between the affected components. But that's not the only interesting effect of distance. There's another one, and that's the components' life cycles. In other words, distance affects how interrelated are their life cycles. As they are located closer to each other, the higher the chances that change in one of them will inadvertently lead to changes in other components. For example, if you are changing a method of a class, chances are that change can affect other methods in the same class, right? And the closer these components are, the higher the probability of such collateral cascading changes. Furthermore, if components share the same life cycle, they have to be tested and deployed simultaneously. And that couples them even more in another dimension. So that's, again, further limits the possibility to evolve them independently. Now, interestingly, lifecycle coupling is affected not only by the type of encapsulation boundaries between these components, but also by the organizational structure of the company that implements them. For example, say we are on that right side. We have two microservices. Now compare two scenarios. The first one is we have two microservices implemented by the same team. Second one, we have two microservices implemented by two different teams. In the latter case, we definitely have higher coordination overhead and lower lifecycle coupling. Thus, we have larger distance, despite the fact that we're talking about the same level of abstraction between them. So another question for me is from me. Let's say we have two systems, and we have that functional coupling between them. Now, since these are two systems, we have large distance between them. And my question is, I know it sounds bad, but what do you think? Is this design necessarily good or bad? Is it necessarily bad? Is it good? It depends. Okay, let me ask you another question. If a tree falls in a forest and no one is around to hear it fall, does it make a sound? It creates vibrations in the air, but that's not a sound technically. So if strongly coupled components never change, who cares about that strength of that coupling, right? Or as Ornelas said yesterday, how can you envision the modularization of the monolith if you don't understand where the product is heading? We have to take that into account here as well. So that takes us to the third dimension, the dimension of time or volatility. And the main question here is, how often do the coupled components actually change? And, well, as the saying goes, it's difficult to make predictions, especially about the future, but we can use some tools to try and estimate the rates at which components are going to change in the future. We can use them to try to identify those components that are expected to change the most. So if we are talking about domain-driven design, of course we have subdomains. According to domain-driven design, business domain is composed of those business building blocks. These define fine-grained functionalities that are required for the company to succeed. And what is interesting for us here is that not all of them are equal. We have three types of subdomains. We have core, generic, and supporting subdomains. Core is all about the company's competitive advantage. These are inventions, optimizations, or intellectual properties that differentiate the company from its competitors. This is how the company plans to make profits. Generic subdomains are the solved problems. These are problems that have accepted solutions that you can just buy or adopt from open source. It's going to be cheaper than to try and implement it yourself. Now, since these solutions are available to everyone, there is no differentiation here, so no competitive advantage. And finally, supporting subdomains are somewhere in the middle. There are no ready-made solutions for them, but they still do not provide any competitive advantage. So supporting subdomains, they're not going to get as much attention from the business as core subdomains. The business is not that interested in optimizing them over time. And that makes core subdomains most volatile. Business is interested in changing them frequently to make sure that they're optimized, to make sure that the solution that is being provided to the company's customers provides the best level of service possible that eventually will lead to maximum profits. So when we evaluate coupling between components, it's important to assess the expected rates of change. And one way of doing it is to analyze the subdomains at play. If there's a core subdomain, that's where we should expect high rates of changes. Yesterday, Suzanne showed us another way of evaluating the expected volatility, and that's wordly maps. Suzanne showed us that if you build a wordly map of your business domain, if you are located on the left, you should expect the most changes, whereas on the right, there will be fewer changes. No political pun intended. So overall, these are the three dimensions of coupling that describe the nature of that relationship between connected components. Now let's see what insights can we gain by combining them together. That's the interesting part. First, strength and volatility. The higher the strength, the higher the probability of cascading changes. The higher the volatility, the more often we'll have to take care of those cascading changes. So when both are high, we get a high maintenance effort. Strength and distance. Distancing the components physically increases the coordination effort needed to implement a change that affects both components. High integration strength over high distance makes that system expensive to change and to evolve. And distance and volatility, these two reflect the coordination effort needed to evolve the system. If both are high, expect communication overload, frequent communication between those different teams implementing those components. Now, that's not the whole picture. To get the whole picture, we need to combine three of them together. And that gives us pain. Remember, I told you that we'll talk about pain? Here it is. So combining all three dimensions together allows us to estimate the pain we are going to endure by maintaining that relationships between the components. Now, stated simply, that maintenance pain is the strength of the relationship times the volatility of the relationship times the distance between these components. Meaning that if all three are high, well, you are going to suffer some pain in your future. Now, following this mathematical thinking, if you wanted to avoid this pain, all you have to do is to minimize one of these values, right? If one of them is 0, then the whole equation is 0, and you have no pain. If you can reduce the integration strength to the minimum, for example, contract coupling, then it's okay to have high volatility over high distance. Cascading changes will require lots of collaboration efforts, but the minimal strength is going to minimize the number of such cascading changes happening. If both integration strength and volatility are high, there is nothing you can do about it. For example, if you have components that are naturally functionally coupled, they implement closely related business functionality, no matter how many hoops through the air you will do, they will still be functionally coupled. You cannot reduce it to, for example, contract coupling. So what you can do in such case is minimize the distance so that cascading changes won't require so much coordination efforts. And finally, if the volatility is 0, high strength over high distance won't really affect you because, they do not change. That's why, for example, if it's okay to be implementation coupled to a legacy system, you can access its database directly, not big deal. If you know that those implementation details are not going to change, then it's okay. It's okay to round that corner. So to sum it up, the algorithm to minimize the pain is to eliminate all accidental coupling, reduce that integration strength as much as possible in that concrete case, and if all else fails, reduce the distance between components between components that have high strength and high volatility. Bring them closer to each other. Now, let's see a couple of examples of this approach in action. First, the integration strength model. Let's say that we know that accessing another microservices database directly is a big no-no. What level of integration strength is that? What do you think? Sorry? Model? Other option? Implementation? Other? Functional? One left? Okay, let's. So first of all, if that database was never intended for integration and its authors are not aware of that integration taking place, that's implementation coupling. Now, let's say that the teams implementing these components decided that we don't care about design. We want to work with the same database because we're working on the same data. In that case, that's functional coupling. If, on the other hand, component A is a BI system that just fetches data from operational database, and the developers of that operational system are aware of it, that's model coupling. That BI system is coupled to the model that is being used by those engineers working on the operational system. And finally, let's say that we have a data mesh, and that database contains data that is intended for integration. For example, it is populated with data which is optimized for data analysis. In that case, that's integration contract. And it's not necessarily a big no-no. Again, data mesh. Now, let's see how we can use this model to explain different patterns and practices from domain-driven design. And first one is an aggregate. We have an aggregate, and we know that it's a transactional boundary, meaning that its contents are working on the same data. That data has to change together, atomically. That makes the contents of the aggregate functionally coupled. At least, it can be also implementation coupled. We usually implement aggregates for core subdomains, so volatility is high. And domain-driven design says you have to balance that by bringing them into the same boundary of an aggregate. Distance is 0, pain is 0, life is good. Bounded context. We know that a bounded context is a boundary of a model, so we have a slightly higher integration strength, higher than contract. It is balanced by the reduced distance. We have that boundary of a bounded context. Again, balanced. Pain is 0, life is good. Supporting subdomains. We know that for supporting subdomains, we can use some rapid application development framework just to get stuff done and forget about it. The strength that can result from such design can be high. The distance, who knows what's going on there? But we know that supporting subdomains, they do not change frequently, so volatility is 0, the relationship is balanced, pain is 0, life is good. Finally, anti-corruption layer, open host service, published language, all these patterns are used to protect the models that are used in a core subdomain. So core subdomain volatility is high. Using them reduces the integration to a contract, which is optimized for integration, so strength is 0. Since we are talking about integration between multiple bounded contexts, the distance is high. Overall, strength is 0, pain is 0, life is good. And with that, we can wrap this whole thing up. And I am almost on time. I have a minute. So coupling, it defines a relationship between a system's components. And my takeaway message is that it's an inherent part of system design. It's not your enemy. It happens in 3 dimensions: strength, volatility, and distance. We talked about this integration strength model that you can use to evaluate the different relationships. We spoke about distance, the fact that the physical distance between components affects the coordination effort that is needed to change them, and it also affects the components' life cycles. And volatility, this one defines how frequent are those cascading changes. We can use different models for assessing the expected volatility of components. And we can combine all three dimensions to evaluate maintenance pain. If you don't want a pain in your future, make one of them 0. Now, if you attended my talk at KanDDD Europe, you know that's not the whole picture. So if you want to get the whole picture, you have to watch the recording when it's going to be available, or you have to be really optimistic and wait for this book to get published. Don't ask me when. Right now, I'm in this death fight with this book. Either I'm going to finish it early next year, or it's going to finish me. Someone is going to be victorious in that fight, okay? Overall, in the book, you will find more details about this integration strength model, where it came from, how it relates to Kinescence, how to compare the same levels of integration strength. For example, if you have two integrations of the same type, for example, model coupling, how you can compare them. I guess we don't have time for questions. So I will say, no, before I say thank you, wait a second. I want to take a selfie with you. Let's do it. Thank you.